Stand in the middle of Kansas today, and nothing about the landscape suggests ocean. Flat fields, dry wind, endless farmland. But beneath that ground are the bones of animals that should not exist there. A farmer once pulled the jaw of a marine predator from a wheat field, not near a coastline, not buried beneath a beach, in the center of America, because 85 million years ago, this entire region was underwater. A warm inland sea split North America in half, stretching from the Arctic Ocean to the Gulf of Mexico, and inside it lived creatures evolution never built again. Predators longer than buses, reptiles with necks too long to look real, fish large enough to swallow prey whole and die trying, and then the sea vanished. Not mythically, not mysteriously, just gone. But the ground still remembers it. How does an ocean disappear from the middle of a continent? And what happens to a world built entirely around it when it does? In this video, we uncover the lost sea that turned the heart of America into one of the strangest ecosystems in Earth's history. If this is your kind of thing, hit like and subscribe. It costs nothing, and it keeps this channel going. Let's begin. Long before the plains carried wheat, highways, and telephone lines stretching toward a flat horizon, the center of North America moved beneath water that glowed green beneath the sun. The Western Interior Seaway spread through the continent during the late Cretaceous, existing from roughly 100 million to 66 million years ago, a broad inland ocean resting where dry grassland now lies. It reached from the cold Arctic in the north to the warm Gulf waters far to the south, dividing the continent into two separate land masses for millions of years without interruption. To the west stood La Remedia, narrow and mountainous, pressed against the edge of the young Pacific. To the east lay Appalachia, lower and older, bordered by the ancestral Atlantic. Between them drifted a shallow sea, larger than the modern Mediterranean, nearly 1,000 kilometers across at its widest point and extending almost 3,000 kilometers from north to south. From above, the continent would have appeared split open down its center by a long tropical corridor filled with light. The water itself was not especially deep. In many regions, the seafloor rested only 100 to 800 meters below the surface, shallow enough for sunlight to penetrate through much of the upper column. Warm currents moved slowly through the basin beneath skies untouched by polar ice. Global sea levels stood 100 to 200 meters higher than they do in the present world, and the continental interior sat low enough for seawater to flood across it for immense spans of time. The shoreline shifted constantly, advancing and retreating over mudflats, river mouths, and mangrove like forests that disappeared beneath tides carrying sediment from distant highlands. Far to the west, the first stages of the Laramide orogeny began lifting stone upward into what would one day become the Rocky Mountains. Those rising mountains altered everything around them. Rivers carried enormous loads of sand, clay, and mineral-rich sediment eastward into the seaway, clouding coastal waters and reshaping shorelines, generation after generation. The western margin of the sea never stayed still for long. Barrier islands emerged and vanished. Deltas spread outward, then drowned beneath new surges of water. Entire ecosystems shifted with the changing edge of the continent. Inside this warm inland ocean, isolation quietly transformed evolution itself. The seaway acted almost like a world separated from the rest of the planet, enclosed enough for species to adapt along paths found nowhere else. Currents circulated through the basin with limited exchange to the wider oceans, creating stable conditions over millions of years. Nutrients washed constantly from nearby land, feeding blooms of plankton that thickened the water with life. Small organisms multiplied in impossible numbers beneath the surface, supporting fish, reptiles, cephalopods, and flying hunters above them in layers of astonishing density. Every level of the ecosystem rested upon abundance. Sunlight entered shallow tropical water almost year round. Sediment carried minerals into the basin. Shorelines provided nurseries for smaller life forms. The sea became productive on a scale difficult to picture in the modern world, rich enough to sustain giants, and stable enough to let them thrive for ages longer than human civilization has existed. For nearly 30 million years, the middle of North America was not land interrupted by water. It was water interrupted by islands of land, a continent reorganized around a warm inland sea that built an entirely separate living world within its shifting shores. Far below the shifting bands of light near the surface, movement traveled through the seaway in sudden silver bursts. Schools of smaller fish turned almost simultaneously, bodies folding into new shapes as they reacted to pressure changes in the water around them. Sometimes the disturbance passed harmlessly into the distance. Sometimes something immense arrived from beneath, accelerating upward with terrifying speed before the school could fully divide. Xiphectinus audax moved through this inland sea long before the largest marine reptiles came to dominate it. It was not a shark, though its size and behavior filled a similar role. Xiphectinus belonged to the teleosts, the great lineage of advanced bony fish that today includes tarpon, tuna, and salmon, yet no living teleost has ever reached quite the same form. At nearly 6 meters in length, it carried the proportions of a predator built entirely around momentum and appetite. Its body was deep through the chest and narrow toward the tail, packed with heavy muscle capable of explosive acceleration in open water. The jaws projected slightly upward in a permanent underbite, lined with long teeth shaped less for slicing than for holding, each tooth curved inward like a hook. Once prey entered the mouth, escape became almost impossible. Rather than tearing flesh apart piece by piece, Xiphactinus swallowed victims whole, relying on size and force to overpower them before they could struggle free. Fossils discovered across the old boundaries of the seaway reveal how widely it ranged. Remains have emerged from Kansas chalk, Alabama sediments, and Canadian rock formations in Alberta, suggesting a predator comfortable across nearly the entire inland ocean. Some specimens preserve vertebrae and fin rays so sharply that the fish still appears poised in motion, as though it simply paused inside stone rather than died within it. One fossil became especially famous among paleontologists because it captured not only death, but the final moments before it. In western Kansas, researchers uncovered a nearly complete Xiphectinus skeleton with another fish preserved inside its body cavity. The prey was a Gillicus, approximately 1.8 meters long, resting inside the predator exactly where it had been swallowed. The smaller fish remained almost entirely intact. No acid etching marked the bones. No digestion had begun. The evidence suggested an abrupt end. Shortly after swallowing the massive prey, Xiphectinus itself died. Some researchers believe the Gillicus continued thrashing violently inside the stomach, rupturing tissue or damaging organs beyond repair. In the dense and competitive ecology of the seaway, even successful feeding carried risk. Survival depended not only on catching prey, but on surviving the process of consumption itself. The shape of Xiphectinus suggests a hunter adapted for both pursuit and ambush. Its tail generated strong thrust in open water, while the large head and forward-facing jaws allowed rapid strikes against schooling fish near the surface. Some paleontologists suspect it occasionally breached from the water during attacks, carrying enormous momentum upward through tightly packed prey schools before crashing back into the sea. For millions of years, Cephactinus occupied one of the highest predatory levels in the Western Interior Seaway. It consumed almost anything small enough to seize, crossed enormous distances through warm interior waters, and carried few visible signs of vulnerability. Yet in this ocean, size alone did not place a creature beyond danger. Sometimes only the head appeared first. A narrow skull, no larger than that of a modern crocodile, would rise quietly through the surface water, inhale, and slip beneath again with almost no disturbance at all. The rest of the animal remained hidden below, suspended in darker layers of the seaway, where its enormous body moved slowly beneath drifting shoals of fish. Styxosaurus snowia belonged to the plesiosaurs, a lineage entirely separate from dinosaurs and fish, descended instead from reptiles that returned to marine life roughly 200 million years earlier. Over immense spans of time, their limbs transformed into long flippers, their bodies flattened into hydrodynamic shapes, and their lives became fully tied to the ocean. By the late Cretaceous, the plesiosaurs of the Western Interior Seaway had divided into dramatically different forms. Some evolved short necks and massive skulls built for crushing prey. Others followed a stranger path, stretching the neck farther and farther until it became the defining structure of the animal itself. Among these long necks, Styxosaurus reached an extreme almost difficult to visualize in motion. The full animal measured approximately 11 meters from snout to tail, yet more than half that length belonged to the neck alone. Up to 6 meters of vertebrae extended forward from the body in a long flexible column containing 72 separate neck bones, more than any known animal in the fossil record. Earlier illustrations often imagined this neck whipping through the water like a serpent, curling sharply from side to side during pursuit. Modern biomechanical studies suggest something quieter and more restrained. The vertebrae allowed gradual curves and controlled movement, but not violent lateral strikes. The neck appears to have functioned less as a weapon and more as a form of distance. Styxosaurus likely remained below schools of fish while extending only its head upward into them, keeping the larger bulk of its body concealed in dimmer water beneath. A small predator entering a school creates less panic than a massive torso with four powerful flippers. In this way, the neck became a stealth adaptation, allowing the animal to approach prey without fully revealing itself until the final instant. Fossils from the Smoky Hill chalk preserve these creatures in remarkable detail, their vertebrae arranged like strings of pale beads through the rock of western Kansas. Some related plesiosaurs preserve stomach contents inside the rib cage, including fish bones and fragments of small ammonites. Mixed among them are gastroliths, smooth, polished stones swallowed deliberately and carried within the body. Their exact purpose remains debated, though many researchers believe they acted as ballast, helping stabilize buoyancy while the animal drifted through different depths. Despite their reptilian ancestry, plesiosaurs did not crawl ashore between dives. Styxosaurus breathed air and surfaced periodically the way whales do now, lifting its narrow head briefly above the inland sea before descending again into warmer currents below. The motion would have repeated thousands of times across a lifetime, quiet and rhythmic beneath skies that no longer exist. In the broad interior waters of Cretaceous North America, Styxosaurus moved with the slow confidence of a mature hunter, gliding through suspended clouds of life with a body plan unlike anything alive in modern oceans. Yet even an animal shaped by millions of years of marine adaptation traveled through waters already occupied by larger appetites. The first mosasaurs did not begin as rulers of open water. Their ancestors moved across shorelines on four limbs, carrying their weight over coastal ground beneath cycads and conifer forests that bordered the ancient sea. They belong to the great lizard lineage, closer to modern monitor lizards than to crocodiles or dinosaurs, with flexible bodies, sharp recurved teeth, and tongues that sampled the air for chemical traces drifting through the environment. Somewhere around 95 million years ago, one branch of these terrestrial reptiles began spending more time near the water's edge. The transition was gradual enough that the fossil record still preserves moments between worlds. Early mosasaurs retained limbs that looked only partly adapted for swimming, feet still capable of spreading into digits rather than forming true paddles. Their nostrils sat near the front of the snout, positioned for an animal lifting only the tip of its face above water while hunting close to shore. Generation after generation, the body changed. The torso lengthened into a more streamlined form, limbs broadened and flattened. Vertebrae near the tail developed taller neural spines that supported stronger swimming muscles. What began as a shoreline hunter became increasingly committed to deeper marine life, until the old terrestrial anatomy nearly vanished beneath new adaptations shaped entirely by the physics of water. For many years, mosasaurs were imagined moving like giant sea snakes, bodies undulating in long waves from head to tail. More recent fossil discoveries have altered that picture. Several exceptionally preserved specimens reveal a downward bend near the tail tip, evidence that the tail supported a crescent shaped fluke similar in principle to that of sharks. Propulsion likely came from powerful tail strokes concentrated near the rear of the body, allowing greater efficiency and speed across open water. The rest of the spine remained comparatively stable during swimming, reducing drag while the tail generated thrust behind it. Despite their increasingly fish like outline, mosasaurs never stopped being air breathers. They carried lungs rather than gills and returned regularly to the surface to inhale. A large individual emerging from darker water would have exposed only a narrow line of skull and nostrils before descending again beneath the surface. Their lives unfolded between two environments at once, dependent on the sea for movement and hunting, yet still tied to the atmosphere above it. The bones themselves preserve traces of how active these animals became. Thin cross sections studied under microscopes reveal fibrolamellar tissue, dense with blood vessel canals and patterns associated with rapid growth. Instead of the slow seasonal development common in many reptiles, mosasaurs appear to have grown continuously and quickly, sustaining high metabolic demands throughout life. Chemical analysis of oxygen isotopes inside tooth enamel strengthens the picture further. The temperature recorded during enamel formation remained consistently warmer than surrounding seawater, suggesting that mosasaurs generated internal heat rather than relying entirely on sunlight or ambient conditions. This transformed the ecology of the seaway. These were not sluggish reptiles drifting passively through warm currents. They hunted actively in dim water, pursued prey over distance, and remained capable of sustained movement even during cooler intervals or nighttime conditions. Within less than 20 million years of entering the marine environment, mosasaurs expanded into nearly every large predatory role available in the inland sea, and among them, one lineage grew beyond all the others, carrying the transformation to its furthest extreme. In certain layers of Kansas chalk, paleontologists sometimes uncover vertebrae so large that the bones resemble sections of carved stone columns rather than the remains of an animal. Nearby lie fragments of ribs curved like ship timbers, and jaws lined with teeth thick as a human hand. When assembled together, the skeleton stretches across an entire laboratory floor. The creature those bones belonged to once crossed the inland sea with the scale and authority of a moving coastline. Tylosaurus proriger grew to lengths between 12 and 14 meters, with body masses estimated from 5,000 to 8,000 kilograms. It was the largest predator known from the Western Interior Seaway, a marine reptile whose range covered much of what is now Kansas, Nebraska, and South Dakota. During the late Cretaceous, the geographic center of modern North America formed part of its hunting territory, open water extending above regions that would remain submerged for millions of years. The skull alone approached 2 meters in length and ended in a distinctive projecting snout that extended beyond the front teeth. This elongated rostrum appears to have functioned as more than ornament. Damage patterns on fossil skulls suggest Tylosaurus may have used the reinforced snout to strike prey before biting, stunning animals with sudden impact. In the same way, some modern dolphins ram targets underwater. The head itself carried a formidable set of teeth, conical and heavily built, suited for gripping struggling prey rather than slicing flesh away in pieces. Inside the mouth, another adaptation waited deeper in the throat. Along the roof of the palate sat rows of pterygoid teeth, angled backward toward the stomach. Once prey entered the jaws, these secondary teeth helped pull it inward through repeated movements of the skull and throat muscles. The process resembled a conveyor, moving food steadily backward, making escape increasingly impossible with every motion. The stomach contents preserved inside Tylosaurus fossils reveal a predator with remarkably little dietary restraint. Researchers have identified remains of large bony fish, sharks, marine birds, smaller mosasaurs, and plesiosaurs within the abdominal cavities of different individuals. One specimen preserves evidence that a Tylosaurus consumed a Styxosaurus, swallowing portions of the long-necked reptile that once moved silently through the same waters. In this ecosystem, even large predators existed within another predator's range. Its sensory abilities appear equally refined. The eyes were proportionally large, suggesting strong vision in dim conditions deeper below the surface. Recent CT studies of related mosasaur skulls show inner ear structures adapted for detecting low-frequency vibrations moving through water. Tylosaurus likely sensed movement at distances beyond visual range, perceiving the displacement of prey through the sea before shapes became visible. The skin covering this enormous body survives in rare impressions preserved within chalk deposits. Instead of smooth, whale-like flesh, the surface carried small diamond-shaped scales similar to those of living monitor lizards. Chemical traces of melanin, preserved in some specimens, suggest countershading across the body, darker coloration along the back, and lighter tones beneath. The same pattern appears repeatedly among modern marine hunters because it reduces visibility from both above and below, allowing a large predator to dissolve into surrounding water. Tylosaurus occupied the uppermost level of the seaway food web for millions of years, moving through warm interior oceans with few limitations imposed by size or competition. Yet the inland sea remained vast enough to support other predators evolving beside it, each shaped toward a different way of ruling the same water. By the final chapters of the Western Interior Seaway, mosasaurs no longer represented a single kind of hunter. They had spread through the ecosystem the way water spreads through connected channels, dividing into specialized forms that occupied nearly every predatory role available in the inland ocean. At least a dozen distinct genera lived at the same time, sharing the same sea while rarely living the same life. Some remained near the brighter upper layers, where fish moved in dense migrating bands beneath the surface. Others descended into darker depths where pressure increased and oxygen levels dropped low enough to exclude many competitors. The seaway had become partitioned vertically as much as geographically, with different mosasaurs adapted to different regions of the water column. Plate carpus belonged to the deeper world. Reaching approximately 7 meters in length, it possessed unusually large eyes relative to skull size, suggesting a hunter dependent on vision in dim conditions. Fossil evidence indicates it likely spent significant time below the better oxygenated surface layers, moving through colder and darker water where fewer large predators operated effectively. The lower portions of the seaway were not empty, but they were quieter, and Platecarpus appears to have evolved specifically for that silence. Its body remained streamlined and flexible, suited for long movement through depth rather than sudden collisions near the surface. Closer to the light moved Cladastes, a much smaller mosasaur, generally measuring only 3 to 4 meters long. Its skeleton was slender throughout, with narrower jaws and a more lightly built frame than larger relatives. Everything about the animal suggests speed. Paleontologists often compare its ecological role to that of a modern short-fin mako shark, pursuing fast-moving fish through open water with bursts of rapid acceleration. In a sea crowded with giant predators, Cladastes survived through agility and precision rather than overwhelming force. Not all mosasaurs hunted soft-bodied prey. Globidens evolved one of the strangest dentitions in the entire seaway. Instead of pointed gripping teeth, its jaws carried rounded crushing structures shaped almost like stone marbles. These globe-shaped teeth specialized the animal for durophagy, the consumption of heavily armored prey. Ammonites, clams, and even hard-shelled turtles could be cracked apart beneath its bite pressure. Fragments of broken shell found near Globidens fossils suggest feeding grounds littered with crushed remains scattered across the seafloor. Then there was Prognathodon, broad-skulled and heavily muscled, carrying one of the strongest bites among known mosasaurs. Estimates, based on jaw mechanics, suggest pressures rivaling or exceeding those of large crocodilians. Where Tylosaurus often subdued prey through momentum and swallowing, Prognathodon possessed the anatomical force to fracture and dismember large animals directly. Its teeth were thick, reinforced, and resistant to stress, allowing it to process prey others might avoid entirely. What unfolded across the seaway was one of the fastest, large-body adaptive radiations known in vertebrate history. In less than 20 million years, descendants of shoreline lizards diversified into deep divers, pursuit hunters, shell crushers, ambush predators, and apex macropredators. The process mirrors later evolutionary expansions among whales and dolphins tens of millions of years afterward, though achieved through entirely different ancestry. Such diversity required extraordinary biological productivity beneath the surface. A sea capable of sustaining so many large predators simultaneously must also have sustained immense populations of prey, layered through every depth and habitat across the inland basin. The water itself had become densely occupied, every level shaped by appetite, movement, and competition carried out beneath the long Cretaceous sky. Above the warm inland waters, shadows crossed the surface with wing beats so slow they almost seemed disconnected from gravity. The animals casting them were neither birds nor bats, but flying reptiles whose proportions still appear improbable even when assembled from complete skeletons. For millions of years, the air above the Western Interior Seaway belonged to pterosaurs, creatures that transformed skin, bone, and muscle into structures capable of carrying enormous bodies across continental distances. The most common among them was Pteranodon longiceps. Thousands of specimens have been recovered from the chalk deposits of Kansas, more than any other large pterosaur known from North America. Some individuals carried wingspans of only 3.5 meters, while the largest males reached nearly 7. The variation reflected dramatic sexual dimorphism. Males possessed proportionally larger bodies and elongated cranial crests projecting backward from the skull in sweeping blades of bone. The exact purpose of these crests remains uncertain. They may have functioned in visual display, species recognition, aerodynamic stability, or several roles at once, shaped by both natural and sexual selection over time. Pteranodon lacked teeth entirely. Its jaws formed a long, tapered beak with sharp edges suited for gripping slippery prey near the surface of the sea. Many paleontologists believe it fed through plunge diving and low skimming flight, descending toward fish in motions somewhat comparable to modern gannets, though on a vastly larger scale. Once airborne, the animal traveled with remarkable efficiency. Despite wingspans wider than many small aircraft, the skeleton remained extraordinarily light. Thin walled bones, enclosed air, filled spaces throughout the body, reducing mass while maintaining strength through intricate internal bracing. Estimates suggest an adult pteranodon weighed only 20 to 25 kilograms. Another pterosaur drifted through the same skies, carrying an even stranger silhouette. Nyctosaurus was smaller in body size, yet supported one of the most extravagant cranial structures ever evolved by a vertebrate. Its crest extended many times higher than the skull itself, branching upward like antlers or spars rising from a ship. No preserved soft tissue connects between the branches, though some researchers have proposed the possibility of a membrane sail stretching across the structure during life. Whatever its exact appearance, the crest suggests functions still not fully understood, combining display, balance, and perhaps aerodynamic influence into a single extraordinary adaptation. Farther south, along the margins of the Seaway, lived Quetzalcoatlus northropi, the largest flying animal known in Earth's history. Its wingspan reached approximately 10 to 11 meters, broad enough to rival small modern aircraft. Unlike Pteranodon, Quetzalcoatlus appears to have spent much of its life on land rather than feeding directly from marine waters. Fossil proportions indicate a tall, long-limbed animal capable of walking efficiently across floodplains and coastal environments, stalking smaller vertebrates through shallow wetlands. When launching into flight, it likely used all four limbs simultaneously, vaulting upward with immense force before transitioning into soaring motion. The skies above the Seaway contained no true equivalent in the modern world. Large seabirds still cross oceans today, but none approach the dimensions or anatomical strangeness of these reptiles. They occupied the atmosphere with the same evolutionary intensity that mosasaurs brought to the water below, filling aerial niches for millions of years above the inland sea. Every layer of this ecosystem had become inhabited by specialists, from the deepest channels to the moving air itself, each shaped toward a different method of survival within the same ancient world. Drifting through the inland sea in numbers beyond counting were animals that carried their homes around them in spirals of calcium carbonate. They floated through the Western Interior Seaway long before the rise of mosasaurs and continued multiplying beneath them afterward, becoming so abundant that their remains eventually settled into entire layers of the seafloor. In many parts of the ancient basin, the water itself would have contained more ammonites than large vertebrates. Ammonites were cephalopod mollusks, distant relatives of the modern nautilus, though far more varied in form and behavior. Their lineage stretched back more than 300 million years, surviving repeated planetary crises that erased countless other groups from Earth's oceans. By the late Cretaceous, they had diversified into hundreds of species across the globe, each adapted to slightly different depths, feeding strategies, and movement patterns. The Western Interior Seaway became one of their richest environments. Their shells served as far more than armor. Inside each coil, Thin internal walls divided the shell into a sequence of chambers. As the animal grew, it moved forward into larger compartments while sealing older chambers behind it. These empty spaces filled with carefully regulated mixtures of gas and fluid, controlled through a narrow tube called the siphuncle. By adjusting the chemistry within the chambers, ammonites controlled buoyancy with remarkable precision, rising or descending through the water column while expending minimal energy. The range of size among ammonites was enormous. Some species possessed shells smaller than a coin, drifting almost invisibly among plankton near the surface. Others reached astonishing proportions. Parapazosia sepenridensis grew shells up to 2.5 meters across, broad spirals approaching the diameter of a large truck tire. Suspended in water, such an animal would have appeared less like a mollusk and more like a slowly rotating wheel moving through the sea. Not all ammonites coiled tightly into spirals. Baculites followed an entirely different geometry. Its shell extended in a long straight column reaching nearly 2 meters in length, tapering gradually toward one end. Paleontologists believe baculites often floated vertically, head downward beneath the shell, moving through the water like a living spear suspended in slow motion. Their fossils occur in extraordinary numbers across Pierre Shale, deposits in the Dakotas and Nebraska, entire ancient populations preserved together beneath layers of marine sediment. The shells themselves preserve evidence of constant predation. Many ammonite fossils carry punctures, fractures, and repaired injuries matching the tooth patterns of mosasaurs. Globidens, with its rounded, crushing dentition, appears especially linked to ammonite abundance. Its entire feeding strategy may have evolved in response to the vast quantities of shelled prey drifting through the seaway. Ammonites also changed rapidly through time. Individual species often survived only 1 to 3 million years before disappearing and being replaced by slightly different descendants. Because these transitions occurred so consistently, paleontologists use ammonite species as chronological markers, identifying the relative ages of rock layers with remarkable precision based on which shell forms appear inside them. Their abundance reflected the immense fertility of the sea itself. Blooms of phytoplankton spread through sunlit waters in colossal quantities, supporting zooplankton, small fish, ammonites, and eventually the giant predators above them. The entire ecosystem rested on microscopic life, multiplying continuously beneath the surface. For millions of years, ammonites remained among the most successful animals on Earth, adapting through catastrophe after catastrophe while oceans changed around them. Their shells accumulated by the millions across the seafloor of North America, silent records of a lineage that seemed almost impossible to erase. Near the deeper floor of the seaway, where suspended particles drifted slowly downward through colder water, a shape wider than many modern cars moved with deliberate calm. Its flippers rose and fell in broad strokes that barely disturbed the surrounding current. Unlike the sleek predators cutting through open water above, this animal carried its mass heavily, almost solemnly, as though the sea itself had slowed around it. Archelon iskyros was the largest turtle known to have lived, reaching approximately 4.6 meters from head to tail, with front flippers spanning nearly 5 meters across. Estimates place its weight above 2,000 kilograms. Fossils recovered from the Pierre Shale of South Dakota preserve the remains of these giants in sediments that once formed part of the seaway floor, where mud accumulated quietly beneath ancient marine currents. At first glance, Archelon resembled a turtle enlarged beyond ordinary proportion, yet much of its anatomy differed from the rigid shell structure people associate with modern land turtles. Its carapace was not a solid dome of fused armor plates. Instead, the shell formed a lighter framework of bony struts covered in leathery skin, similar in principle to the modern leatherback sea turtle. This reduced weight and likely improved flexibility and buoyancy in open water, allowing such a massive reptile to travel efficiently across long distances. The head ended in a strongly hooked beak rather than teeth, where patterns along the jaws suggest a diet focused on softer prey. Jellyfish drifting through the water column may have formed a major food source, along with soft bodied ammonites and decaying carcasses sinking from above. Archelon did not need to overpower large prey to survive. It occupied a slower ecological rhythm, feeding steadily in a sea crowded with far more aggressive hunters. One famous specimen preserves evidence of just how dangerous those waters remained. The skeleton lacked its right rear flipper, severed long before death, yet the surrounding bone had fully healed. The animal survived the injury for years afterward. Many paleontologists suspect the missing limb resulted from an attack by a large mosasaur, perhaps even Tylosaurus itself. The turtle escaped, adapted, and continued living through the immense interior ocean despite the loss. Growth patterns within Archelon bones reveal another unusual possibility. During cooler seasonal periods, individuals may have settled near the seafloor and entered states of dramatically reduced metabolic activity. Rather than remaining constantly active, the turtle could conserve energy for extended intervals, resting almost motionless in darker water while conditions above shifted through seasonal cycles. Its enormous size served as its greatest protection. Fully grown Archelon presented an awkward target, broad and heavy enough that many predators may have judged an attack too costly in energy or risk. It shared the seaway with fast pursuit hunters, giant marine reptiles, and diving predators from above, yet survived not through speed or aggression, but through endurance and scale. The lineage behind Archelon stretched far deeper into time than the seaway itself. Sea turtles had already existed since the Triassic, persisting through environmental changes that erased countless other groups. Archelon carried that ancient inheritance into one of the strangest marine ecosystems Earth ever produced, moving slowly through waters crowded with specialized giants while remaining profoundly unlike any of them. Its survival depended less on dominance than persistence, a quieter strategy that often lasts longer in the history of life. At certain moments, the surface of the seaway must have resembled a gathering place for impossible lineages. Reptiles crossed beneath the water, pterosaurs circled overhead, and among them moved birds whose anatomy still carried traces of a much older evolutionary world. Their feathers would have appeared familiar from a distance, yet inside their jaws sat rows of teeth, small and sharp against the soft tissues of the mouth. Hesperornis regalis belonged to a group now called the Hesperornithines, diving birds that abandoned flight almost entirely in favor of underwater hunting. Fully grown individuals reached approximately 1.8 meters in length, comparable to the height of a tall human when stretched from head to feet. The body resembled an extreme interpretation of a modern loon, elongated, streamlined, and specialized for life in water above nearly everything else. Its wings had shrunk into vestigial remnants too small for powered flight. Evolution redirected energy and muscle away from the air and into the rear limbs instead. The legs grew large and powerful, positioned far back on the body where they functioned as underwater propellers. While swimming, Hesperornis likely pursued fish through rapid strokes of the feet, steering with subtle movements of the torso and neck beneath the surface. Inside the jaws, grooves held numerous pointed teeth unlike anything seen in modern birds. These teeth were not embedded in separate sockets the way crocodilian teeth are, but arranged in channels along the bone itself. Their purpose was straightforward and effective, gripping slippery prey during underwater pursuit. Fish scales and vertebrae discovered near fossil specimens support the image of an active aquatic hunter feeding primarily below the surface rather than above it. The same anatomical changes that improved swimming made movement on land extremely awkward. Hesperornis probably could not stand upright in the way seabirds do today. Like living loons, it may have dragged itself forward using its legs and belly whenever forced onto shore. Most of its life unfolded in water, resting on the surface between dives or disappearing beneath it in search of prey. Fossils found from Kansas to the Canadian Arctic show that Hesperornis ranged across nearly the entire length of the seaway, occupying waters thousands of kilometers apart within the same inland marine system. It became one more specialized predator layered into the immense ecological complexity of the Cretaceous interior. Another bird shared the same skies and coastlines while following a very different evolutionary path. Ichthyornis dispar remained capable of true powered flight, smaller in size and more agile in the air, roughly comparable to a modern tern, yet it too possessed teeth. Paleontologists believe Ichthyornis hunted by plunge diving into the water from above, combining aerial maneuverability with fish catching adaptations similar to those of later seabirds. The contrast between these two animals captures an unusual moment in avian history. One lineage surrendered flight in exchange for underwater efficiency. Another retained flight while refining aerial hunting strategies. Both still carried teeth inherited from ancient ancestors, a feature destined to disappear entirely from birds within only a few million years. The seaway supported them both simultaneously, allowing radically different solutions to emerge inside the same environment. Feathers, teeth, flippers, shells, and elongated jaws all existed together within one ecosystem, each representing a separate answer to the challenge of survival in the inland sea. Life here did not move toward a single design, it expanded outward into every workable form the environment could sustain. For a long time, the private lives of plesiosaurs remained hidden behind a simple uncertainty. Their bodies were fully adapted to the ocean, yet they still breathed air. That single fact carried an unresolved problem through paleontology for generations. Somewhere in the life cycle of these marine reptiles, reproduction had to occur, and no one knew whether that moment belonged to the land or the sea. Modern sea turtles solve the problem by hauling themselves ashore. Whales and dolphins solve it differently, remaining in the water for birth itself. Plesiosaurs seemed suspended uneasily between those possibilities, their anatomy offering hints in both directions. The long flippers that moved them so gracefully through open water would have made crawling onto beaches difficult and exhausting. Yet, until direct evidence appeared, uncertainty remained. Then a fossil from Kansas altered the discussion permanently. In 2011, researchers studying a specimen of Polycotylus latipinus discovered something preserved inside the rib cage of the adult animal. Within the body cavity rested the skeleton of an embryo, articulated and remarkably complete. The smaller skeleton measured roughly one-third the size of the mother, already large and well developed before birth. The proportions mattered immediately. Egg-laying reptiles generally produce many small offspring, investing less energy into each individual. The embryo inside Polycotylus followed the opposite pattern. It was enormous relative to the adult body, carrying developmental characteristics far closer to live-bearing mammals such as dolphins and orcas than to reptiles nesting on shorelines. The fossil became the first direct evidence that at least some plesiosaurs gave birth to living young within the water itself. That discovery transformed the image of these animals. A fully aquatic reproductive strategy meant plesiosaurs never needed to drag themselves onto land at vulnerable moments in their lives. Birth, growth, feeding, migration, and death could all occur entirely within the marine environment. The inland sea was not simply where they hunted, it was where every stage of existence unfolded. The presence of only one large embryo also suggested something deeper about behavior. Producing a single offspring requires enormous biological investment. Energy that might otherwise create dozens of smaller young becomes concentrated into one developing individual with a much higher chance of survival after birth. Among living animals, this pattern frequently correlates with extended parental care and social interaction. Orcas protect calves for years. Elephants remain within family groups for decades. Even some modern reptiles guard nests or offspring for limited periods despite far simpler social structures. No fossil can directly preserve behavior with complete certainty, yet the implications widened the emotional complexity of the seaway ecosystem. Plesiosaurs may not have lived only as solitary hunters crossing empty water. Young animals could have traveled beside adults for extended intervals. Smaller individuals may have remained protected within groups while learning migration routes or feeding behaviors. A mother surfacing for air in the ancient sea may have risen, accompanied by a calf swimming close beside her. The evidence remains fragmentary, but even fragments alter the atmosphere of the world being reconstructed. The seaway increasingly resembles not a collection of isolated monsters, but a layered biological community shaped by relationships, communication, and long developmental lives unfolding beneath the surface. Across distant spans of geological time, evolution often arrives repeatedly at similar solutions when faced with similar environmental demands. Warm-blooded activity, live birth, streamlined movement, parental investment, and complex marine behavior emerged here long before whales inherited comparable roles in later oceans. Seen separately, the animals of the seaway appear wildly different from one another. One lineage began as lizards walking coastal ground. Another descended from ancient reptiles, already committed to marine life, long before the first dinosaurs appeared. Birds entered the water through feathers and hollow bones. Giant fish followed entirely different anatomical histories. Yet when their skeletons are placed beside modern marine animals, familiar patterns begin to emerge with strange consistency. The mosasaurs provide one of the clearest examples. Their ancestors had nothing to do with whales or dolphins. They evolved from reptiles, not mammals, and entered the ocean tens of millions of years earlier. Even so, their bodies gradually transformed toward a recognizable marine design. The torso lengthened into a hydrodynamic shape, limbs flattened into steering surfaces. The tail developed a fluke capable of efficient propulsion through open water. Later whale lineages would arrive at nearly the same arrangement independently, starting from entirely different terrestrial ancestors and separated by immense stretches of geological time. Plesiosaurs followed a different route yet arrived at similarly familiar outcomes. Evidence for live birth and possible parental care places them unexpectedly close to modern dolphins and orcas in behavioral strategy, despite the evolutionary gulf between them. The environment itself favored certain solutions. Large aquatic animals that breathe air benefit from protecting fewer, more developed offspring capable of surviving immediately in open water. Over time, unrelated lineages repeatedly converge toward the same reproductive patterns because the ocean imposes similar demands on survival. The diving birds of the seaway reveal the same principle in another form. Hesperornis abandoned flight and redirected its anatomy toward underwater propulsion using the legs. Modern loons, grebes, and penguins later evolved comparable movement strategies despite sharing no direct ancestry with those Cretaceous birds. Long bodies, rear positioned limbs, and streamlined swimming posture appear again and again whenever vertebrates adapt to pursuing prey beneath the surface. Even Gephactinus carried echoes of modern oceans. Its feeding style relied on seizing and swallowing large prey whole, a strategy mirrored today in animals such as tarpon and Goliath grouper. Certain mechanical solutions simply continue working across time. Fast prey requires sudden acceleration. Open water favors streamlined movement. Deep diving rewards oxygen efficiency and thermal regulation. Evolution works within the boundaries imposed by physics, and those boundaries remain remarkably stable even as species change. This recurring process is known as convergent evolution, though the phrase itself only names something larger and quieter. Life repeatedly discovers similar shapes because water repeatedly asks the same questions of every organism entering it. Movement through a dense fluid requires efficiency. Hunting in dim environments rewards sensory specialization. Breathing air while living at sea encourages surfacing behaviors, buoyancy control, and energy conservation. Across millions of years, unrelated animals continue arriving at overlapping anatomical answers because the ocean narrows the range of forms that truly function well within it. The Western Interior Seaway preserves one of the most complete demonstrations of this principle in the fossil record. Inside a relatively isolated inland ocean, evolution independently rebuilt body plans and behaviors that had appeared before and would appear again later in entirely separate groups. The repetition was not accidental. It emerged from environmental pressure acting steadily across enormous spans of time, shaping flesh toward workable designs again and again. The result is a strange familiarity running through vanished worlds. Beneath the alien anatomy and extinct names, many seaway creatures already carried outlines that the oceans would eventually rediscover in later ages through entirely different bloodlines. Life changed constantly, yet the sea kept steering it toward recognizable forms. In western Kansas, the land occasionally opens into pale cliffs that look almost weightless under afternoon light. The rock breaks apart easily beneath wind and rain, soft enough in places to crumble between fingers. From a distance, the bluffs appear quiet and nearly empty, but the stone holds one of the densest fossil records of ancient marine life ever discovered on Earth. This formation is known as the Smoky Hill Chalk, part of the larger Niobrara Formation spread across portions of the Great Plains. Exposures emerge through Gove, Logan, and Trego counties, where erosion has stripped away younger sediment and uncovered layers deposited during the height of the inland sea. The chalk itself formed between roughly 87 and 82 million years ago, preserving a 5 million year interval from the center of the seaway's long existence. The substance of the rock began as drifting life so small it could barely be seen. Coccolithophores, microscopic marine algae encased in delicate calcium carbonate plates, bloomed continuously through the warm surface waters. When they died, their shells descended in immense quantities toward the sea floor below. For millions of years, this silent accumulation continued, layer settling upon layer until entire beds of marine sediment formed from the remains of organisms smaller than grains of dust. Pressure slowly compressed those deposits into chalk hundreds of meters thick. Within that pale stone lies nearly every major creature of the seaway. Tylosaurus skeletons emerge with jaws still articulated. Styxosaurus vertebrae curve through slabs in long sequences, Xiphactinus appears frozen in violent motion, sometimes preserving prey inside the body cavity itself. Pteranodon wings stretch outward through the rock in thin black impressions. Archelon, Hesperornis, sharks, fish, ammonites, and countless smaller organisms recur across the formation again and again, not as isolated accidents, but as part of a sustained ecological archive. The remarkable condition of these fossils depends largely on the chemistry of the ancient seafloor. In many regions of the seaway, bottom waters contained very little oxygen. Carcasses sinking into these depths encountered fewer scavengers and slower bacterial decay than in oxygen rich marine environments. Bodies often settled undisturbed into soft sediment where burial occurred before currents or feeding animals could scatter the bones. Because of this, articulation remains unusually common. Entire skeletons preserve the original arrangement of vertebrae, ribs, flippers, and skulls rather than collapsing into disordered fragments. Even delicate structures sometimes survived. Skin impressions from mosasaurs record scale patterns across the body's surface. Fossil stomach contents reveal final meals consumed shortly before death. One plesiosaur specimen preserved an embryo inside the mother's rib cage. In rare cases, traces of organic pigment compounds still linger chemically within the stone, despite the passage of tens of millions of years. The formation continues changing even now. Rain cuts narrow channels through the bluffs. Winter freezes widen fractures. Wind carries away loosened sediment grain by grain. Every season exposes new material that had remained sealed underground since the late Cretaceous. Professional paleontologists still work these deposits extensively, but many important discoveries have also come from amateur collectors, moving carefully across the chalk with permits and practiced patience. The Smoky Hill chalk functions almost like a preserved memory of the inland sea itself, held not in written language, but in mineral layers built from vanished organisms and buried tides. The ocean disappeared, yet the sea floor remained behind, lifted slowly into open air, where the ancient world could eventually surface again, bone by bone. Long before laboratories could read isotope ratios or trace pigments preserved inside fossilized skin, the inland sea passed through the hands of two paleontologists whose rivalry reshaped American science. Edward Drinker Cope and Othniel Charles Marsh uncovered much of the Western Interior Seaway's fossil record during the late 19th century, but their discoveries emerged through distrust, competition, and personal hatred, intense enough to damage nearly everyone involved. The two men did not begin as enemies. During the 1860s, they exchanged fossils, praised one another publicly, and even named species after each other. Both understood that the expanding American West contained ancient bone beds unlike anything yet studied in Europe. Kansas, in particular, became a magnet for expeditions. Railroads cut through chalk deposits filled with marine reptiles, giant fish, and flying reptiles preserved beneath the plains. Each new excavation carried the possibility of discovering a species no human being had ever seen before. The fracture between them began with Elasmosaurus, a long-necked plesiosaur related to Styxosaurus. Cope reconstructed the skeleton incorrectly, mounting the skull at the end of the tail instead of the neck. Marsh recognized the mistake immediately and exposed it publicly among scientific circles. The humiliation spread through newspapers, journals, and professional meetings. Cope attempted to withdraw the flawed publication, but copies had already circulated. The resentment hardened permanently after that moment. What followed became known as the Bone Wars. Both men sent collectors into the field not only to excavate fossils, but also to spy on rival crews. Workers were bribed for information about promising dig sites. Local guides secretly redirected shipments of fossils away from competitors. In several reported incidents, valuable deposits were deliberately damaged with explosives rather than left for the opposing side to collect. Scientific fieldwork began resembling industrial sabotage conducted across the chalk bluffs of the American frontier. The pressure to claim discovery rights accelerated everything further. Marsh and Cope published descriptions of incomplete skeletons with reckless speed, sometimes announcing new species before the surrounding rock had been fully removed. Mistakes entered the scientific record constantly, yet the volume of material they uncovered remained extraordinary. Between them, they named more than 130 prehistoric species, including many animals that defined the seaway itself. The rivalry consumed both careers. Marsh exhausted institutional support and lost political influence connected to federal geological surveys. Cope spent enormous personal wealth financing expeditions and eventually sold much of his fossil collection to settle debts. By the ends of their lives, both men had become isolated figures, surrounded by crates of bones, unfinished manuscripts, and fading reputations. The fossils endured more gracefully than the people who fought over them. Skeletons collected during the Bone Wars still occupy museum collections, where modern paleontologists continue studying them with technologies unknown to the 19th century. CT imaging reveals hidden anatomical structures inside stone. Microscopic bone analysis reconstructs growth rates and metabolism. Chemical traces preserved within fossils retain evidence of coloration, diet, and body temperature. The ancient sea survived the rivalry intact within the chalk, patient beneath the ambitions of everyone who tried to possess it. What Cope and Marsh treated as trophies gradually became something quieter, a long scientific archive capable of revealing new details, each passing generation of researchers. A fossil no longer ends where the visible bone ends. Modern paleontology has learned to extract information from stone that 19th century collectors would have considered impossible, reading microscopic structures and preserved chemistry, the way earlier scientists once read only shape and size. The animals of the seaway have become more detailed with time rather than less, as though the chalk continued storing hidden layers of memory beneath the surface of the skeleton itself. One of the most revealing methods begins by slicing fossil bone into sections thin enough for light to pass through. Under a microscope, the interior structure becomes visible in concentric growth bands, similar to tree rings. Bone histology allows researchers to estimate how rapidly an individual grew, how old it was when it died, and what kind of metabolism sustained its life. In mosasaurs, those microscopic patterns appear dense and fibrolamellar, a tissue structure associated today with birds and mammals rather than slow-growing reptiles. The bone suggests prolonged activity, rapid growth, and energy demands far above those of modern crocodilians or lizards. Chemical analysis of tooth enamel deepens the picture further. Oxygen isotopes locked into enamel crystals preserve a record of the temperature at which the tissue formed. When scientists measured mosasaur teeth, the ratios consistently indicated body temperatures several degrees warmer than the surrounding seawater. The implication altered the image of these animals entirely. They were not sluggish marine reptiles dependent solely on sunlight for warmth, but active predators capable of generating internal heat while hunting through open water. Other discoveries emerged from fossils once considered little more than curiosities. In 2014, researchers used mass spectrometry on preserved mosasaur skin and identified eumelanin, the same pigment responsible for dark coloration in many living animals. The chemistry pointed toward countershading, darker across the upper body and lighter beneath, a camouflage pattern shared today by sharks, dolphins, and tuna. The seaway's predators were not merely gigantic, they were visually adapted to disappear into shifting marine light. Scale impressions preserved within the chalk reveal surface textures in remarkable detail. Mosasaur skin consisted of small, diamond-shaped scales arranged without overlap, closely resembling the skin of modern monitor lizards. Variations appeared around the face and flippers, suggesting specialized regions of flexibility and hydrodynamic control. Even the tongue left traces behind. Grooves preserved within certain skull bones closely match the divided tongue structure of living varanid lizards, indicating that mosasaurs almost certainly possessed forked tongues capable of chemoreception. They likely sampled dissolved chemical particles in the water, tracking prey through scent as much as sight. The stone preserves evidence of feeding with equal precision. Fossilized stomach contents reveal fish bones, bird remains, ammonite shell fragments, and smaller marine reptiles swallowed shortly before death. Jaw muscle attachment scars allow estimates of bite force and feeding mechanics, reconstructing predator-prey interactions no human being ever witnessed directly. Even coprolites, fossilized feces preserved within marine sediment, contain fish scales, shark cartilage, and crushed shell fragments that confirm dietary habits independently from teeth alone. The seaway grows more vivid with every analytical tool brought against it. Microscopes, isotope, chemistry, and imaging technology continue uncovering details hidden inside fossils for tens of millions of years. The ancient sea increasingly resembles a recoverable world rather than a distant abstraction, its creatures emerging not only as skeletons but as living organisms with body heat, coloration, feeding behavior, and sensory systems shaped by the water they moved through. The end of the Western Interior Seaway did not arrive as a single catastrophe descending suddenly across the continent. For millions of years before the final extinction event, the inland ocean had already begun withdrawing from the land that once held it. The transformation unfolded slowly enough that no living creature within the ecosystem could have perceived the full scale of the change. Yet the geological record preserves the retreat with quiet precision. Far to the west, the crust of North America was rising. The Laramide orogeny, the prolonged mountain-building episode that eventually produced the modern Rocky Mountains, altered the shape of the continent itself. Sediment accumulated along newly elevated regions, while the western interior gradually tilted upward. Water that had once spread broadly across the middle of the continent began shifting northward and southward as the basin lost its ability to hold such an immense sea. At the same time, global sea levels were falling. During much of the Cretaceous, Earth existed without major polar ice caps, allowing oceans to remain dramatically higher than today. By the final few million years of the period, planetary conditions had begun changing. The worldwide reduction in sea level compounded the effects of rising land, narrowing coastlines, and reducing the reach of shallow marine environments across the continental interior. The seaway slowly fragmented into separate bodies of water. In the north, a shrinking remnant known today as the Cannonball Sea persisted for a time near the Arctic connection. Farther south, another marine basin remained linked to the Gulf of Mexico. Between them, former stretches of open ocean transformed into coastal plain, estuary, swamp, and river system. Areas that once supported mosasaurs and ammonites gradually filled with sediment carried eastward from the young mountains. As the water became shallower, its chemistry changed as well. River systems pouring into the remaining basins diluted seawater with increasing amounts of fresh water, creating brackish conditions stressful to highly specialized marine organisms adapted to stable salinity. Warmer shallow water also held less dissolved oxygen, further straining ecosystems already under pressure from habitat loss. The Great Migration ranges that once extended from Arctic waters to the Gulf Coast narrowed dramatically. Populations became isolated within shrinking marine corridors. Predators that had crossed thousands of kilometers in search of prey found themselves compressed into smaller regions where food resources declined even as competition intensified. Ecological compression reshaped the food web from the bottom upward. Fewer stable habitats meant fewer prey species, and fewer prey species destabilized the giant predators that depended on them. The retreat survives visibly in the rock itself. Layers of open marine chalk deposited in deep offshore conditions gradually transition upward into sandy shoreline limestone. Above those appear mudstones formed in floodplains and swamp deposits rich in organic material that would eventually become coal. The changing sequence records a continent replacing ocean, with land step by step across immense spans of time. By 66 million years ago, the Seaway no longer resembled the vast tropical system that had once divided North America into separate landmasses. It had become fragmented, shallow, chemically unstable, and biologically diminished. The ancient inland sea was already weakened before the final disaster arrived. The extinction that followed did not erase a thriving ecosystem at its height. It struck a world already retreating from itself, a sea that had begun forgetting its former scale long before the last day came. Long before the first effects reached the Western Interior Seaway, a mountain-sized object was already descending through Earth's atmosphere faster than any living thing had ever moved. The Chicxulub impactor, a bolide estimated between 10 and 15 kilometers wide, crossed the final distance to the planet in seconds, striking the shallow carbonate platform of what is now the Yucatan Peninsula at nearly 20 kilometers per second. The collision released energy on a scale difficult for the human mind to hold steadily. Current estimates place it near 100 teratons of TNT, roughly 1 billion times more powerful than the Hiroshima bomb. Rock beneath the impact site did not merely shatter, it vaporized instantly. The crust itself became expanding plasma, excavating a crater almost 180 kilometers across while ejecting molten debris beyond the atmosphere. The location of the strike mattered enormously. The bolide hit shallow marine sediments rich in sulfur and carbonate minerals. Billions of tons of pulverized rock, sulfur dioxide, water vapor, and incandescent ejecta blasted upward into the stratosphere in less time than a human lifetime takes to draw breath. Around the planet, fragments of molten material began falling back through the atmosphere on ballistic arcs, reheating the sky as they descended. Within hours, much of the northern hemisphere experienced a radiant heat pulse. Forests ignited. Dry vegetation combusted across entire continents. Soot from global wildfires joined the expanding layer of dust and sulfur already spreading through the upper atmosphere. Oceans reflected a dim, red sky filled with drifting particles, while ash settled onto coastlines and inland rivers alike. Yet the greatest damage came not from fire, nor from the shockwave itself, but from darkness. Over the following days and weeks, the atmosphere thickened with aerosols dense enough to block a catastrophic fraction of incoming sunlight. Photosynthesis collapsed across land and sea. In the oceans, phytoplankton populations began dying first. These microscopic organisms had formed the energetic foundation of the marine ecosystem for millions of years. Their disappearance spread upward through the food web with brutal efficiency. Zooplankton populations crashed soon afterward. Small fish and juvenile marine animals lost their primary food source. Predators that depended on those fish continued hunting for a time inside a shrinking biological system already exhausting itself. The collapse moved silently through the seaway, trophic level by trophic level, until even the largest hunters encountered emptier water. Mosasaurs, despite their dominance, required enormous and continuous caloric intake to sustain fast growth, active swimming, and elevated metabolism. Large predators often survive longest during ecological collapse because stored energy reserves delay starvation, yet the end still arrives when prey populations fail entirely. The last mosasaurs likely persisted for months after the impact before disappearing from the fossil record forever. The Ammonites vanished as well. For more than 300 million years, they had endured repeated planetary crises, surviving extinctions that erased countless other lineages. Their dependence on productive surface waters became fatal in a darkened ocean. Within the extinction horizon, every ammonite species on Earth disappeared. Some creatures endured. Sea turtles and crocodilians survived partly because survival demanded less from them. Lower metabolic requirements, broader diets, and the ability to persist for long periods without food allowed scattered populations to outlast the collapse. The Western Interior Seaway, already diminished by retreating waters and ecological strain, faded completely from the world that followed. Its predators vanished, its skies emptied, its currents slowed into silence beneath a darkened atmosphere that lingered over Earth for years. After the final mosasaur disappeared and the last ammonite shell settled into dark sediment, the oceans did not remain empty for long. Water rarely tolerates vacancy. Currents continue moving. Sunlight still falls across the surface, and evolution begins testing new forms almost immediately, shaping survivors into whatever the sea can still support. The Western Interior Seaway itself was gone by then, drained into memory and stone, yet the ecological spaces once occupied inside it remained open across the global ocean. Roughly 16 million years after the extinction, small mammals living along river margins in what is now South Asia began entering shallow water more frequently. These animals, called pachycetids, were not dramatic creatures. They resembled lean deer with elongated skulls and limbs still built for land. Their footprints pressed into muddy shorelines while fish moved through nearby channels. Nothing in their appearance suggested the future return of giant marine predators. Yet, evolution had solved this transition before. Over millions of years, the descendants of those mammals changed in ways eerily familiar to the ancient patterns once seen in mosasaurs. Their limbs shortened and broadened into paddles, their spines elongated, their bodies narrowed into streamlined forms suited for sustained swimming. Nostrils migrated upward and backward across the skull. Tails became the primary source of propulsion. By approximately 50 million years ago, fully aquatic whales were moving through open seas with the same fluid efficiency that marine reptiles had mastered tens of millions of years earlier. Basilosaurus emerged from this transformation as one of the first giant whale predators. Reaching lengths near 18 meters, it hunted fish and smaller whales through warm Eocene oceans. Its role in the ecosystem strongly echoed the vanished Tylosaurus, not because the two animals shared ancestry, but because large marine predators encounter the same physical demands regardless of origin. Efficient movement through water always narrows evolution toward similar answers. Other niches filled just as predictably. Deep diving predators returned in the form of sperm whales, descending more than 2,000 meters beneath the surface in pursuit of squid through cold darkness. Their ability to exploit the lower water column recalls the ecological role once occupied by plate carpus in the ancient seaway, where enlarged eyes and specialized anatomy allowed hunting beneath brighter surface layers. Fast pursuit hunters also reappeared. Dolphins and orcas evolved high intelligence, social coordination, and sustained speed in open water. Their cooperative hunting strategies mirror patterns suspected in some plesiosaurs and resemble the streamlined pursuit adaptations once seen in smaller mosasaurs like Cladastes. The actors were mammals now rather than reptiles, yet the ocean continued rebuilding familiar behaviors from entirely different biological foundations. Sea turtles endured as well. Archelon itself vanished with the extinction, but modern leatherback turtles still cross immense distances beneath open skies, carrying flexible, leathery shells rather than rigid armored domes. Their silhouettes preserve an echo of a world otherwise erased. Above the surface, pterosaurs never returned. Their aerial territories passed instead to seabirds. Albatrosses inherited long distance soaring over open water. Gannets and boobies became plunge divers of extraordinary precision. Penguins and cormorants transformed wings into underwater propulsion systems, pursuing fish beneath cold currents in ways convergent with far older divers. The oceans rebuilt themselves gradually from survivors and newcomers alike. Different lineages entered the water, encountered the same environmental pressures, and arrived once more at familiar shapes. The seaway's world disappeared completely, yet its functional patterns endured, repeating across ages as though the planet remembered them. Long after the last mosasaur drifted into extinction and the final waves withdrew from the continent's interior, the Western Interior Seaway remained behind in altered form, folded quietly into the structure of the land itself. Its presence persists beneath wheat fields, highways, reservoirs, and towns spread across the center of North America. The ancient sea no longer reflects sunlight, yet nearly every layer beneath the Great Plains still carries its imprint. Much of the petroleum extracted from Kansas, Oklahoma, Nebraska, and Texas began as microscopic life suspended in warm Cretaceous water. Immense blooms of phytoplankton once drifted near the surface of the seaway, converting sunlight into organic matter with extraordinary efficiency. When those organisms died, countless trillions settled slowly toward the bottom, joining a continuous rain of biological debris that accumulated over millions of years. Buried beneath younger sediment, compressed by pressure and transformed by geothermal heat, those ancient carbon deposits gradually became oil and natural gas. Every reservoir tapped from mid-continent shale formations is therefore connected to vanished plankton communities that floated through a tropical inland sea more than 66 million years ago. The fuel burned in engines and furnaces today contains carbon that once passed through living cells suspended beneath Cretaceous sunlight. The shape of the land also reflects the sea that occupied it. For tens of millions of years, fine marine sediments accumulated across the continental interior in enormous thicknesses. Mud, carbonate particles, and microscopic skeletal remains settled continuously through calm water, smoothing irregularities in the basin below. Later, uplift and erosion exposed these deposits as broad plains rather than jagged terrain. The apparent simplicity of the modern Great Plains emerged partly from the patient leveling action of an ocean that no longer exists. Freshwater systems inherited this buried architecture. The Ogallala Aquifer one of the most important groundwater reserves in North America, rests above sedimentary layers linked to the seaway's geological history. Water now moves through porous deposits shaped by processes that began beneath marine conditions long before human agriculture appeared on the continent. Cornfields, cattle pastures, and irrigated farmland depend indirectly upon sediments deposited under ancient saltwater skies. In western Kansas, pale chalk bluffs continue rising above dry grasslands. Across the Dakotas, the Pierre Shale erodes into fractured badlands beneath winter snow and summer heat. In Colorado, the dark slopes of the Mancos Shale weather slowly under wind and rain. These formations are not symbolic reminders of the seaway. They are its actual floor, lifted into open air and still surrendering fossils from within their layers. The modern image of Middle America as permanently landlocked exists only within a narrow human perspective. For most of the last 100 million years, this region has changed repeatedly between shallow sea, coastal marsh, delta plain, river system, and grassland. Landscapes that appear stable across human generations shift constantly when measured against geological time. Permanence is largely an illusion created by short lifespans and inherited memory. The plains seem eternal because civilizations rise and vanish too quickly to witness continental transformation directly. Yet beneath the quiet fields of the interior, the evidence remains everywhere. Shell fragments still weather from exposed rock. Marine sediments still underlie farms and cities. The continent remembers the sea that once divided it, even after the water itself has gone. Beneath the grasslands and highways of central North America, the continent still carries the structural memory of water. The basin that once held the Western Interior Seaway did not vanish when the sea withdrew. It remains embedded within the shape of the crust itself, quiet beneath farms, cities, aquifers, and sediment layers accumulated across immense spans of time. The question of whether the sea could return is therefore not fantasy nor catastrophe in the cinematic sense, but geology unfolding at its customary pace. For an epicontinental sea to flood the continental interior again, two conditions must occur simultaneously. Global sea levels must rise dramatically, and the interior of the continent must subside low enough for marine water to advance inland across thousands of kilometers. During the late Cretaceous, both circumstances aligned for millions of years. Polar ice was minimal or absent, allowing sea levels to stand between 100 and 200 meters higher than today, while tectonic forces created a broad low basin through the center of the continent. Modern climate projections, even under severe warming scenarios, operate on a far smaller scale. Current estimates suggest sea level rise of roughly 1 to 2 meters by the year 2100, with additional increases over subsequent centuries if polar ice sheets continue destabilizing. Such changes would profoundly affect coastlines, estuaries, and low-lying cities, yet they remain vastly insufficient to flood regions as elevated and distant from the coast as Kansas or Nebraska. The deeper processes that create inland seas move with extraordinary slowness. Continents rise and sink over tens of millions of years through tectonic loading, crustal stretching, mantle dynamics, and erosion. The Rocky Mountains, which now form part of the Western Barrier, preventing marine flooding into the continental interior, are not permanent structures. Wind, rivers, freeze cycles, and gravity are gradually wearing them down, grain by grain. Though the change is imperceptible within human history, geological time measures mountains differently. Peaks eventually become hills, and hills become sediment. Sea levels themselves also cycle repeatedly across Earth's history. The Cretaceous world was not unique in possessing high oceans. Numerous periods in the geological record show marine transgressions advancing far across continental interiors under warmer climates and altered tectonic configurations. The dry landscape, familiar today, represents only one temporary arrangement among many others the continent has already experienced. No scientist can assign a meaningful future date to the return of an inland sea across North America because the processes involved unfold on scales extending beyond civilization itself. 10 million years is a short interval, geologically. 100 million years is not extraordinary. Human cities, languages, and political borders exist inside spans so brief they scarcely register against tectonic motion. Yet the rock record leaves little ambiguity about the larger pattern. The modern continent is not fixed into its present form. The plains were once submerged beneath warm salt water filled with ammonites, mosasaurs, and drifting plankton blooms. Before that, they existed as other environments entirely, and after the present grasslands disappear, they will become something else again. The Western Interior Seaway, therefore, belongs not only to the past, but to an ongoing planetary cycle of rising water and shifting land. The sea withdrew, the continent dried, ecosystems changed, and mammals inherited the emptied world. Eventually, under conditions no human civilization will witness, water may once more advance inward across the basin, filling ancient pathways that the continent has never entirely forgotten. Wind continues to uncover the Western Interior Seaway grain by grain. Rain loosens chalk from exposed bluffs. Winter frost fractures shale apart, and entire skeletons that rested untouched for 80 million years slowly emerge into daylight from hillsides that appear empty at first glance. The sea is gone, yet its archive remains active, still surrendering information to anyone patient enough to read it carefully. The fossil formations tied to the seaway remain among the most scientifically productive on Earth. New mosasaur species continue to be identified from deposits stretching across Kansas, South Dakota, and Alabama, including several described within the last decade from specimens discovered not by universities, but by amateur collectors walking exposed terrain beneath open prairie skies. The scale of the formations is so immense that even after more than a century of excavation, only a fraction has been systematically explored. Technology has changed the nature of discovery almost as dramatically as discovery itself. In 2014, researchers applied mass spectrometry to preserved mosasaur skin and identified traces of eumelanin, the same pigment responsible for dark coloration in many living animals today. For the first time, scientists recovered original pigment chemistry from a marine reptile. A creature that once existed only as bone and inference suddenly acquired visible patterning again, darker along the back and lighter below, a camouflage arrangement convergent with modern sharks and dolphins. Other revelations emerged not from chemistry, but from imaging hidden structures inside fossilized skulls. During the 2010s, CT analysis of plate carpus specimens revealed inner ear anatomy adapted for detecting low-frequency underwater sound. This finding altered previous assumptions about mosasaur behavior. Hunting may not have depended entirely on vision or direct pursuit. Vibrations moving through water, perhaps generated by struggling prey or distant movement in darkness, likely formed part of the sensory world these animals inhabited. The pregnant polycotylus specimen, discovered in Kansas, also continues generating new interpretations years after its original description. Researchers examining the embryo, bone growth, and pelvic anatomy increasingly view at least some plesiosaurs as fully aquatic live bearers with extended parental investment. Each reanalysis refines the picture further, suggesting behavioral complexity once considered impossible to recover from fossils alone. Even the invertebrates remain incompletely known. New ammonite species are still being described from Pierre shale exposures, their rapidly evolving shell forms helping paleontologists divide geological time into increasingly precise intervals. The sheer diversity of these animals means entire branches of the seaway's food web remain only partially cataloged despite generations of study. Large portions of the Niobrara Formation remain buried beneath younger sediment or isolated in difficult terrain. Significant volumes of fossil-bearing rock have never been examined directly. Modern fieldwork increasingly uses ground-penetrating radar and LiDAR mapping to identify buried bone concentrations before excavation begins, allowing paleontologists to locate promising sites without disturbing vast sections of landscape blindly. Given the physical scale of the seaway deposits and the density of fossils already recovered, researchers regard future discoveries as statistically inevitable. Entire species almost certainly remain hidden inside untouched chalk layers, waiting within stone that no human eye has yet examined. The seaway, therefore, remains unfinished science. Its creatures continue emerging from erosion and technology together, one through natural exposure, the other through increasingly refined tools capable of extracting information invisible to earlier generations. The ancient ocean still speaks, and each decade broadens the vocabulary through which its vanished world can be understood. A human life is measured in heartbeats, birthdays, fading photographs, and the slow alteration of familiar faces. Even the oldest cities on Earth remain small enough for the mind to hold comfortably. Stone walls weather, languages shift, dynasties vanish. Yet all of recorded civilization occupies only a narrow surface layer atop a planet whose memory extends incomprehensibly deeper. The Western Interior Seaway existed for roughly 25 to 30 million years. That span alone exceeds the entire evolutionary history of primates, from the earliest proto-monkeys to modern humans. Every empire ever raised, every religion formed, every war fought, every scientific discovery made by human beings occupies only a minute fraction of the duration for which that inland sea persisted across North America. Agriculture began approximately 12,000 years ago. Permanent settlements emerged soon after. Written history is younger still. By the time the seaway vanished 66 million years ago, it had already existed for nearly 24 million years. Its extinction, which now appears unimaginably ancient, occurred after a lifespan vastly longer than all of human civilization combined. This is the difficulty of deep time. Geological duration resists ordinary thought because human intuition evolved to navigate immediate scales, migrations, storms, seasons, generations. The nervous system can estimate the passing of hours and years with reasonable accuracy, yet it possesses no instinctive framework for understanding a million years. Numbers that large cease behaving like experience and become abstraction instead. At certain scales, the mind stops visualizing altogether. 1,000 years can still evoke ruins, dynasties, or ancestral memory. 10,000 years begins dissolving into vagueness. 1 million years has no direct experiential equivalent. 25 million years stretches beyond narrative instinct entirely, and 66 million years becomes less a quantity than a kind of darkness beyond familiar perception. Writer John McPhee popularized the modern use of the term deep time, describing the sensation as a vanishing into the abyss. The phrase captures something unsettling and strangely beautiful at once. Geological time does not merely extend farther than human history. It reduces human history to a nearly invisible interval embedded inside a continuum so immense that ordinary chronology loses meaning. And yet, deep time occasionally becomes tangible through physical objects. A mosasaur tooth, recovered from a Kansas riverbank, fits easily inside a human hand. Its enamel still catches light. Its edges remain sharp enough to mark skin lightly if pressed. The tooth feels immediate, material, undeniably real. Holding it collapses a portion of the abyss into something touchable. For a brief moment, the vanished sea ceases being theory or illustration and becomes contact with an organism that hunted in warm inland water tens of millions of years before human beings existed. Beneath the American interior lies an almost continuous geological archive extending back roughly 100 million years. Chalk, shale, sandstone, coal beds, river deposits, ancient soils, each layer records a different world. The strata accumulate not as isolated fragments, but as sequential memory, one environment slowly replacing another through spans of time no living creature could witness directly. Deep time, therefore, alters more than scientific understanding. It destabilizes assumptions about permanence itself. Continents flood and dry repeatedly. Mountains rise and erode away. Entire ecosystems dominate the planet for millions of years and then disappear so completely that only mineral traces remain. The rocks beneath the plains preserve a quiet instruction. Landscapes are not fixed settings for history. They are temporary states inside processes still unfolding, long after human memory ends. From orbit, continents appear stable, immense, fixed into place like pieces of painted stone. Coastlines seem permanent. Mountain ranges feel immovable. Human civilizations inherit landscapes already formed and unconsciously treat them as eternal settings, as though plains and deserts and oceans have always existed in their current arrangement and always will. Yet, geology records a different reality, one in which the surface of Earth behaves less like architecture and more like weather unfolding across immense spans of time. The Himalayas, now carrying glaciers and thin mountain air high above Asia, were once buried beneath the Tethys Sea. Limestone near their summits still contains marine fossils from organisms that drifted through warm water long before the mountains themselves existed. The Alps preserve a similar memory. Shells and seabed sediments became trapped, compressed, and slowly lifted skyward as continents collided over millions of years. Stone that now overlooks valleys and forests was once darkness beneath an ocean surface. Even deserts carry traces of vanished worlds. The Sahara, now defined by dunes and heat shimmering across bare rock, held lakes, rivers, and grasslands within the span of relatively recent human prehistory. Before that, shallow marine water repeatedly advanced across portions of North Africa, retreating and returning through cycles driven by climate and tectonics. Landscapes exchange identities continuously, although the transitions often unfold too slowly for individual generations to notice directly. The Western Interior Seaway was therefore not an isolated curiosity, but a particularly vivid expression of a universal principle. Continental surfaces are temporary states. The land beneath a modern Kansas wheat field has occupied radically different conditions within the last 100 million years. It has been open ocean beneath migrating Ammonites, shallow tropical sea beneath flying pterosaurs, humid coastal swamp thick with vegetation, muddy river floodplain crossed by changing channels, and finally grassland beneath modern wind and sky. Even the mountains that helped destroy the seaway are themselves temporary. The Rocky Mountains continue eroding grain by grain. Rivers carry fragments of them eastward every day, redistributing their stone into plains and basins. 50 million years ago, the Rockies stood higher than they do now. 50 million years from now, they will stand lower still, softened and reduced by weather, gravity, frost, and flowing water. Meanwhile, the Atlantic Ocean widens gradually as tectonic plates drift apart at roughly 2.5 centimeters per year. The motion is imperceptible across a human lifetime, yet over 200 million years it accumulates into continental scale rearrangement. At the same time, the Pacific Ocean contracts through subduction, its crust descending slowly back into Earth's mantle. Geological maps of the distant future suggest that today's continents may eventually converge again into another supercontinent assembled from land masses currently separated by entire oceans. Somewhere within the interior of that future world, rain and subsidence may once again create shallow inland seas. New coastlines may spread across regions that are now dry continental centers. Creatures descended from modern life, altered by millions of years of evolution, could occupy ecological roles that echo the vanished seaway in strange and recognizable ways. The ancient inland ocean was never a final world. It was one moment in an ongoing planetary transformation that began long before humanity and will continue long after every modern border, language, and city has disappeared. Across the history of Earth, life has crossed the boundary between land and sea again and again, not once or twice as isolated accidents, but repeatedly, almost rhythmically, as though evolution keeps rediscovering the same doorway. The Western Interior Seaway was one chapter in that larger movement, a place where ancient coastlines became laboratories for transformation and where terrestrial bodies slowly reshaped themselves for water. Long before the seaway existed, ichthyosaurs entered Triassic oceans and evolved into streamlined predators whose outlines resembled modern tuna and dolphins despite sharing no close ancestry with either. Later came plesiosaurs and mosasaurs, descendants of land reptiles that returned to marine life during the Cretaceous. Tens of millions of years after their extinction, mammals repeated the process. Early whales descended from four-legged ancestors that once walked riverbanks in South Asia. Seals and sea lions followed their own separate route into coastal waters much later still. Each transition produced remarkably similar solutions. Bodies elongated and narrowed to reduce drag. Limbs flattened into paddles or flippers. Vertebral columns adjusted for efficient swimming. Reproduction shifted steadily toward live birth whenever permanent life at sea became advantageous. Metabolism increased in lineages that needed sustained movement through open water. Evolution arrived repeatedly at comparable anatomical answers because the ocean imposed the same physical demands regardless of which lineage entered it. This pattern suggests something profound about marine environments. The sea is not alien to terrestrial life in the way human imagination often frames it. Rather, land and ocean appear as two recurring states between which life moves whenever ecological opportunity and evolutionary pressure align. The boundary separating them is permeable across geological time. Organisms cross it, adapt, diversify, vanish, and are replaced by entirely new lineages that eventually discover similar pathways once more. The seaway's predators, therefore, were not monstrous aberrations belonging to an impossible lost world. They were expressions of a process that has unfolded continuously for hundreds of millions of years. Given available space, sufficient prey, and enough evolutionary time, life repeatedly expands into unoccupied niches and constructs forms capable of surviving there. The resulting creatures may appear extraordinary to human eyes, yet, from the perspective of evolution, they are recurring outcomes shaped by recurring conditions. Their extinction does not make them unreal or failed. Mosasaurs ruled inland seas for roughly 25 million years. That duration exceeds the existence of humanity many thousands of times over. Their world endured long enough for entire ecosystems to evolve, stabilize, diversify, and disappear completely beneath layers of sediment. The fact that nothing living remembers them directly changes nothing about the reality of their existence. Evolution itself contains no preference for permanence. It does not plan toward eternal survival or ideal forms. It builds only for immediate conditions, refining organisms generation by generation according to what works at a particular moment within a particular environment. The mosasaur was perfectly suited to the warm inland oceans of the late Cretaceous, just as the orca is suited to modern seas. Neither represents a final design. Eventually, climates shift, oceans open and close, continents rearrange, and the conditions supporting one form of life dissolve into new possibilities. Species disappear not because evolution stops functioning, but because it continues functioning under altered circumstances. The Seaway's history, therefore, is not ultimately a story about loss. It is a story about continual transformation, about life reshaping itself endlessly as the planet changes around it, carrying the same ancient process forward into worlds not yet formed. A fossil changes the landscape around it even before anyone fully understands what it is. A fragment of vertebra weathering from pale stone, a row of teeth exposed after rain, the curve of an ancient shell emerging from dry earth. Each object quietly contradicts the visible world surrounding it. The plains remain flat. Wind still moves through grass. Roads and fences remain where they were. Yet the meaning of the land alters immediately once the buried past becomes visible. Before the fossils of the Western Interior Seaway were uncovered, the middle of North America was largely understood in simple geographic terms as farmland, prairie, grazing country, open continental interior. The discovery of mosasaurs, plesiosaurs, giant turtles, toothed birds, and marine reptiles transformed that understanding permanently. The continent did not merely contain evidence of ancient life. It contained proof that the landscape itself had once belonged to an entirely different world. Every Tylosaurus tooth pulled from Kansas chalk carries that implication. Every elongated neck vertebra of Styxosaurus and every weathered Archelon flipper bone argues against the assumption that the present condition of Earth is its ordinary or stable form. Fossils reveal that stability is temporary, a passing arrangement mistaken for permanence only because human lifetimes are too short to witness major geological change directly. The bones, therefore, are not relics of a vanished anomaly. They are evidence that there has never been a final version of the world. Oceans advance and retreat, mountains rise and erode away. Ecosystems dominate entire regions for millions of years and disappear so completely that later landscapes seem unrelated to what came before. Fossils preserve moments within that continuous transformation. Paleontology occupies a peculiar position among sciences because it cannot manipulate its subject directly. A physicist may repeat an experiment. A chemist can alter conditions and observe results in real time. Paleontology works differently. It reads traces left behind by processes already completed long before human beings existed. The science advances through interpretation, comparison, excavation, chemistry, and inference, assembling fragments into coherent narratives about worlds no observer ever witnessed. Yet, Those reconstructions reshape the present. A geologist who has spent years studying the Kansas chalk no longer sees wheat fields as merely agricultural terrain. Beneath the surface lies accumulated memory, layers of marine sediment deposited grain by grain beneath warm inland water. The visible landscape becomes only the latest state, resting atop countless earlier ones. In that sense, the monsters of the Seaway leave behind more than skeletons. They leave behind altered perception. After encountering their remains, the world no longer appears fixed or self-explanatory. Land ceases being passive background and becomes an active participant in deep planetary history, temporary and transitional rather than permanent. In 1918, a farmer in Kansas uncovered part of a massive mosasaur jaw while working his field. At first, it appeared only as strange stone emerging from soil. Once identified, however, the discovery permanently changed the conceptual ground beneath that landscape. The farm remained physically identical, yet it could never again be understood as simple prairie isolated from ancient oceans. That may be the most enduring inheritance the Seaway left behind. Not oil trapped in shale, not chalk bluffs weathering under modern rain, not fossils mounted in museum halls, but a question carried quietly through stone itself. A question about how many worlds have already existed here, and how many more still wait beneath the surface of time. The essential mystery of the Western Interior Seaway is no longer biological. Science has identified the major predators, reconstructed food webs, measured body temperatures, analyzed pigments, mapped migrations, and traced evolutionary relationships across entire lineages. The broad outlines of that vanished ecosystem are now visible with remarkable clarity. Yet beneath all those discoveries remains a quieter and more difficult question, one that begins only after the anatomy and chronology are understood. What does it mean that this world existed at all beneath the center of a modern continent? The Seaway destabilizes ordinary assumptions about place because human beings unconsciously divide Earth into fixed categories. Land feels permanent, oceans feel separate and distant. Continents appear stable enough that maps printed centuries ago still resemble the ones used today. Daily life reinforces the illusion that geography is enduring and familiar, that the environments surrounding civilization represent the natural condition of the planet rather than temporary arrangements within longer cycles. An inland sea stretching across North America for 25 million years contradicts that intuition completely. Not briefly, not catastrophically, not as a singular event remembered by witnesses, but as a stable geological condition persisting longer than the entire evolutionary history of primates. Human history measures itself through episodes, wars, dynasties, inventions, migrations. Geological history operates differently. Conditions exist for incomprehensible durations and then gradually become something else. That difference is difficult for the mind to absorb because events possess narratives while conditions often do not. A storm begins and ends. A civilization rises and falls. A sea occupying the center of a continent for millions of years exceeds ordinary storytelling instinct. It simply was, continuously, through spans of time so immense that entire evolutionary lineages emerged, diversified, and vanished while the water still covered the plains. The creatures living there possessed no awareness of their impermanence. A mosasaur, hunting through warm inland currents, was not participating in prehistory from its own perspective. It inhabited a present moment as immediate and ordinary as any experienced by living organisms today. A Tylosaurus surfacing above what is now Kansas was simply breathing in familiar air, beneath familiar light, on another unremarkable afternoon in its world. The astonishment exists only because of the distance separating that moment from this one. Roughly 85 million years stand between the animal and the observer contemplating it. Across that gulf stretches an almost impossible chain of circumstances. The organism had to die in preservable conditions. Sediment had to bury it before destruction. Rock layers had to survive tectonic change, erosion, and deep time. Wind and rain then needed to expose the fossil at precisely the moment a human capable of recognizing its significance encountered it. And somehow that chain succeeded. The tooth rests now behind museum glass. The vertebrae are catalogued. The chemistry of the enamel can still be analyzed. Through fragments of mineralized tissue, a species capable of abstract thought has partially reconstructed the existence of another species separated from it by nearly the entire span of mammalian evolution. That connection may be the most extraordinary aspect of the Seaway. Not merely that giant marine reptiles once crossed the middle of North America, but that knowledge itself could bridge such distance. Stone preserved memory long enough for minds that did not yet exist to eventually recover it. The fossils, therefore, leave behind more than evidence of vanished animals. They leave behind a confrontation with time, continuity, and the fragile improbability of understanding anything beyond the present moment at all. Long before roads, fences, railways, and state borders divided the American interior into recognizable patterns, the ground itself was already carrying memories older than mammals, older than flowering forests, older than the mountains that now frame the horizon to the west. Every landscape visible today rests on previous landscapes buried beneath it, layered one atop another with the slow patience of geological time. Human beings experience the surface only briefly, inheriting a momentary version of Earth and mistaking it for permanence because a human lifetime is too short to witness continents rearranging themselves. The Western Interior Seaway is only one chapter in that deeper history, though it remains among the clearest ever exposed on land. Its traces survive, not merely as fossils displayed behind museum glass, but as the structure of the plains themselves. The pale chalk beds stretching across Kansas, the shale exposures weathering through the Dakotas, the petroleum reservoirs beneath Oklahoma and Texas, all are direct continuations of that vanished sea, translated into modern forms. Ancient plankton became hydrocarbons, seafloor sediment became farmland, marine limestone became the stone beneath highways and towns. A person driving across Nebraska today sees immense horizontal distance, grain silos, irrigation systems, and fields moving in the wind beneath an open sky. Yet, hundreds of meters below those fields lie compressed accumulations of microscopic shells that once drifted through warm Cretaceous water. Beneath those sediments are older layers deposited by earlier rivers, older coastlines, older oceans still. The flatness itself carries the imprint of long vanished marine deposition, millions of years of fine sediment settling through quiet water before later uplift exposed it again to air. The seaway, therefore, has not truly disappeared. It has changed states. Its chemistry persists in fuel refined into gasoline. Its biological productivity survives as carbon reservoirs extracted from rock. Its dead plankton powers engines. Its sediments store groundwater inside aquifers feeding crops across the Great Plains. Even the horizon line bears its influence, softened by marine deposits spread across enormous distances before erosion shaped them into the plains recognized today. Meanwhile, the fossils continue emerging from the chalk with each passing season. Rain loosens another vertebra from a hillside. Wind uncovers another ammonite coil. A rancher notices bone weathering from a bluff where no specimen had been visible the year before. These discoveries are not remnants of a completed science. They are active information entering the present, examined with isotopic analysis, CT imaging, molecular chemistry, and scanning systems unavailable even a decade ago. The ancient sea continues speaking because the rock record has not finished revealing what it contains. And beneath all modern activity, beneath highways and wheat fields and quiet towns illuminated after sunset, the physical bodies of that world still remain entombed in darkness. Mosasaur vertebrae rest inside chalk strata. Shark teeth remain embedded in shale. Fragments of shell lie compressed beneath layers of sediment, accumulated long after the sea withdrew northward and vanished. They remain there even now, silent below the surface, while modern life moves overhead unaware. The ground carries these histories continuously. It remembers tropical oceans beneath grassland, remembers predators crossing inland currents where cattle now graze, remembers conditions so ancient they resist ordinary imagination. The surface changes quickly by comparison. Names change, borders change, civilizations rise and disappear. But beneath them, the earth keeps its older memory intact. At the end of a day, when the room has quieted and the ordinary machinery of life begins slowly dimming, the mind becomes strangely open to scales it resists during waking hours. Geological time enters more easily then. The imagination softens its grip on clocks and schedules and immediate concerns, allowing older things to drift closer. A vanished inland sea crossing the middle of a continent feels less impossible in darkness than it does beneath afternoon sunlight and traffic noise. Perhaps that is because the Western Interior Seaway belonged to a rhythm so much larger than human urgency that it quietly rearranges perspective simply by being considered. 25 million years of warm water spreading from the Arctic to the Gulf existed without hurry. Entire evolutionary lineages appeared, adapted, hunted, reproduced, and disappeared while the sea itself remained, patient and immense, across durations the human nervous system cannot naturally picture. Yet the inability to emotionally grasp such time does not reduce its reality. The water moved there, the chalk settled there, the predators surfaced there to breathe beneath Cretaceous skies now erased. None of those creatures understood themselves as ancient or extraordinary. A mosasaur crossing through dim green water near what would someday become Kansas was not participating in history from its own perspective. It was only alive within the immediate conditions of its world, responding to hunger, movement, light, current, instinct. The Ammonites drifting beneath sunlit surface blooms did not know they were part of a lineage already hundreds of millions of years old. The pterosaurs circling overhead had no awareness that no flying animal larger than they were would ever exist again. Even the stone itself remained unaware. The chalk accumulating grain by grain on the seafloor did not know it was preserving articulated skeletons for distant mammals capable of extracting meaning from buried calcium and compressed time. Preservation happened silently through chemistry and sediment and the absence of oxygen at the bottom of a shallow inland sea. Meaning arrived much later. It arrived when weather exposed bone from bluffs. It arrived when collectors carried fossils from the plains into museums and laboratories. It arrived when scientists learned to read isotope ratios, growth rings, pigment traces, and microscopic structures hidden inside stone. Most of all, it arrived whenever another human mind became capable of holding the impossible sequence together, linking a modern landscape to the world beneath it. That chain of noticing stretches across astonishing distance now. A person lying awake at night can think backward through wheat fields, chalk beds, marine sediment, extinct reptiles, vanished oceans, drifting continents, and impacts from space, then return again to the quiet room where those thoughts are happening. The distance between those 2 points is so large that the fact it can be crossed mentally at all begins to feel unusual in itself. And yet it happens constantly. Knowledge allows vanished worlds to persist in forms they never possessed while alive. The seaway existed first as water and life and motion. Now it exists, additionally, as understanding, carried invisibly through memory, language, science, and imagination from one mind into another. Stone eventually erodes, mountains flatten, oceans withdraw, fossils fracture and weather back into dust. But once something has been understood, even partially, it enters a different kind of survival. Night settles differently on land once covered by an inland sea. The plains appear motionless in darkness. Wheat fields and empty roads stretched beneath the same stars that once reflected from warm Cretaceous water. Yet beneath that apparent stillness, the older world remains physically present, layered below the surface in chalk, shale, buried skeletons, and compressed traces of vanished life. The sea withdrew tens of millions of years ago, but withdrawal is not the same thing as disappearance. Geological history rarely vanishes completely. More often, it changes form and waits. At this moment, somewhere in western Kansas, rainwater is moving slowly across exposed chalk bluffs, carrying away grains of calcium carbonate too small to notice individually. Tiny fractures widen through cycles of heat and cold. Sediment loosens. A vertebra hidden since the late Cretaceous shifts imperceptibly closer to open air. The movement may amount to less than a centimeter in a decade, yet erosion possesses extraordinary patience. Eventually, bone that has remained sealed in stone since before primates existed will emerge beneath modern sunlight. No one can predict who will notice it first. Perhaps a rancher crossing a pasture after a storm. Perhaps a student searching road cuts during summer heat. Perhaps no human at all. For another century, the fossil itself does not hurry toward discovery. It exists within a timescale where decades pass almost invisibly. That scale changes the emotional texture of the present. The Western Interior Seaway endured for approximately 25 million years, an interval so long that the entire history of civilization occupies only a thin fraction beside it. Cities, governments, languages, industries, and generations rise and dissolve rapidly compared with the slow accumulation of marine sediment or the uplift of continental rock. Yet, rather than diminishing human life, this perspective softens its sharpest edges. Urgencies that dominate individual days become smaller when held against a background measured in millions of years. The creatures of the seaway continue existing through consequences that survived them. Their world became stone, their plankton became petroleum, their sediments became farmland and aquifers. Their fossils reshaped scientific understanding of evolution, extinction, anatomy, climate, and geological time. Even now, the ancient sea continues entering the present through laboratories, museums, road cuts, drilling sites, and quiet discoveries weathering from hillsides after rain. The monsters remain part of the living world in another sense as well. Every attempt to imagine what existed before human memory inevitably reaches backward toward them. A child standing before a mosasaur skeleton, a geologist tracing marine strata through the plains, a traveler looking across Kansas and learning an ocean once occupied the horizon, all participate in the continuation of the sea's story. Knowledge preserves environments differently than stone does, carrying them through mines rather than sediment. And so the seaway still exists in layered forms. It exists materially beneath the continent. It exists scientifically through the records extracted from fossils. It exists imaginatively wherever ancient oceans are remembered beneath modern ground. Outside, the land remains quiet. Beneath it, chalk holds its buried archive with the same calm persistence it has maintained for millions of years. The sea rests there still, patient beyond measure, while another night passes above it. There is nothing left now except the silence of deep time and the old ground waiting beneath sleep.